So in this installment of our series, we're going to be covering carbocation rearrangement. Now, before we get into carbocation rearrangement, which I promise is fairly simple, we need to learn about stability within molecules. When we have a carbocation indicated by the positive charge, we want it to be as stable as possible. This is necessary for chemical reactions to occur as efficiently as possible. So, here we can see increasing stability. Now we need to know this before we get into the different types of carbocation rearrangement. So, if stability is actually determined by how many carbons are around our carbocation. So here you see one carbon, here 2 carbons, and here 3 carbons. Now we'll move on to the hydride shift. So now to explain hydride shifts, we will have our fellow teacher, Kevin, make an appearance. Kevin?
So a hydride shift occurs when you have a hydrogen shifting from more substituted carbon to less substituted one, usually the one with the carbocation. So this carbocation has 2 carbons, so it's in a secondary structure. But then you have this carbon right here that has 3 carbons attached to it, so it's tertiary. So you want to shift basically this carbocation from the secondary structure and move it entirely to this third one. So usually what you do is, for these, you have to draw on your own hydrogens are shown. So there's a hydrogen over here, and there's also one over here. So hydride shifts occur when a hydrogen from a more substituted group, this hydrogen over here, shifts to this less substituted group with the carbocation. So you shift this over here. So then this becomes like this. Now it's 4 groups attached to it. Now since it has 4 groups attached to it, the carbocation no longer exists because it's neutral. And then now you look over here, and it has this one has 4 groups, and this one has the carbocation now. Now after the shift, now this carbon has 4 groups attached to it, so it has a neutral charge now. And now the carbocation moved completely from this carbon to this carbon. And after the hydride shift, after this hydrogen moved from here to here, or here to here, this new carbon only has 3 groups attached to it. Now it's a carbocation, but it has 3 groups, so it's a tertiary structure. Rather than before, it was a secondary structure on this one, so that's a hydride shift, and it makes it more stable.
So, a methyl shift is very similar to a hydride shift, except instead of a hydrogen moving, it is a methyl group. So as you can see, this carbocation currently has 2 carbons attached to it, so it's secondary, and this carbon has 4 carbons attached to it, and so if you moved one of these carbons, the carbocation would become more stable. So for the methyl shift, we will move this methyl to this carbon, and when that happens, the carbocation shifts to this one. Well, the methyl, first of all, shifts over here, and the carbocation shifts right there. So as you can see, right now, the carbocation is tertiary, which will be more stable and thus more likely to react. Okay, both the methyl and the hydride shift can only happen to adjacent carbons. So for example, if the carbocation in this example started over here, then nothing can change because you can't move carbons over more than one atom.